So, welcome to this lectures on linear algebra. Last time we have seen direct decomposition, a direct sum decomposition of a vector space and projection maps. I want to do it today for many projections together or for arbitrary direct sum decomposition of a vector space. So, let us start with, let as usual V be a K vector space which has the direct sum decomposition with the direct sum decomposition V is direct sum of UIs. Strictly speaking, I should be writing, instead of this, I should be writing sum I in I UI, where UI is a family of subspaces of V. From this direct sum decomposition, I will define now many projection maps, as many as indexed by this set I. And conversely, if I have a family of projections on V which are indexed by some arbitrary set, then I will get a direct sum decomposition. Precisely this we have done it for two subspaces in last lecture. So, now I want to define for each. So, with this is given to us. So, for every j in I want to define Pj, and that will be projection on V, projection of V. So, it should be a map from V to V, and also with the property that Pj square should be Pj. And obviously, the j should be used somewhere. So, the definition of Pj is, take any element V in V, because V is a direct sum, V has a unique expression like this, summation uj, j in, not uj, I want to use a different index, ui, I in I, where only finitely many UIs can be non-zero, with UI equal to 0 for almost all I in I. If you would have identified this, we have checked that this means this map is an isomorphism. We have identified this, then you do not have to keep writing this sentence for almost all, that is understood. So, map these and these UIs are unique, UI belong to UI, they are uniquely determined by a V. That is the meaning of that V as a direct sum decomposition. So, map this V to the jth component here, uj. This is obviously makes sense, and it is a map from V to V, because these components are uniquely determined by V. Now, we have to check several things. We have to check that Pj is a projection, that means we have to check that Pj square is Pj. So, let us check that first. So, I want to check that Pj square on V, start on any V. So, this is by definition of this Pj, this is Pj of V, but this is Pj of Uj, but Uj is already in Uj. So, this is nothing but Uj, which is Pj of V. So, on every V there Pj square and Pj are equal. So, that this is true for every V in V. So, that proves Pj square equal to Pj. Now, we need to check, now we also need to check what is, I want to say that Pj is along whom. So, that means I need to find out what is the image of Pj. So, Pj will be on to that and it will be along the kernel. So, let us find out what is okay. We need to find out what is image of Pj and also what is kernel of Pj. Then this is precisely the Uj and this is the remaining sum. This is the remaining sum. I in I, but not j, and this is ui. This is also direct sum. So, then we will say that Pj is projection of V onto Uj along this remaining direct sum. That is the language we have been using for projection. Okay, so each what we have defined for each j in I, we have defined a projection Pj. Projection of V onto Uj along the remaining sum. Moreover, this family satisfies some more properties. So, this family of projections Pj satisfies the following properties. Okay, the first one is the summation. I have to be little careful here. Summation I in I Pi. This is IDV. 2 Pi compose Pj is 0 for all indices I and j which are different, I not equal to j. And third one, okay. So, the 2 is easy because you see the Pj has image Uj and Pi has image Ui, but Pi will be 0 on the remaining part. So, it is 0, that is clear. See, if I take P, so to check this I have to check that on any V in V there is 0, but write V as summation Ui I in I, Ui's are in capital Ui's and almost all are 0, almost all are 0. Once you have written V like that, what is Pj of V? That is Uj by definition. When you apply once more Pi, that will be Pi of this, but Pi of Uj is 0 because I is different from j. So, therefore, this composition is 0 is clear. Now, here little bit tricky here. First of all, I have to justify what do I mean by sum, because I may be infinite set, I could be infinite, I may be not finite, and therefore, we have to justify what do we mean by this sum. So, that I do it in the next page. So, Okay. So, first of all note that this I will need this definition again and again. So, let us say take, so this is a general definition which we will need again definition. Let Fi are linear operators on a vector space V, k linear operators indexed by I, or I is in I, this I could be infinite set. Then we say that the family Fi I is summable if for every V in V, Fiv is 0 for almost all I. Only finitely many could be non-zero, and in this case we put summation Fi I in I on V to be this sum. Because of our assumption that it is 0 for almost all I, this sum makes sense. So, therefore, this symbol summation Fi I in I, it is an operator again, this is k linear operator again. This is a map from V to V, and it is very easy to check that this is k linear operator on V. And it will be called a sum operator. On V. So, the most important part is Fi should be 0 for almost all I, and then the sum makes sense, and the sum operator makes sense, and that is called the sum of the family Fi. So, in order to make the earlier part, I will just show you. We want to, so this sum to make sense, we need to verify that Pi on any V is 0 for almost all I, but that is because every V has a decomposition like this, summation Ui, where almost all Ui's are 0. So, only Pi, only whichever component of V are coming, only those will survive. Okay, so therefore, that makes sense, and now we need to verify that this sum is identity, but that is very easy. So, we need to verify that the sum Pi I in I is nothing but the identity operator on V. So, we should check that for any V in V, both the sides are equal. So, you evaluate this Pi I in I on V, and this should be for, by definition it is summation PIV. And what is PIV? PIV will only be when you write V as a finite sum, only those components are coming there. So, this is nothing but summation Ui I in I, but this is V because everything is unique, or V is uniquely written as summation Ui, therefore, this makes sense. So, from the direct sum decomposition, we got the family of projections with these two properties. It is a summable family, their sum is the identity operator and they are pi times pj are 0 where I is different from j. So, these are also called orthogonal family. I do not want to use the term because it is not really necessary to use. Now, I want to do the converse. Conversely, if I start with the projections on a vector space, family of projections which satisfy these two properties, then I get a direct sum decomposition of V. So, that I want to write it as a theorem. So, more generally, I want to state this as a theorem. So, theorem. So, let pi I in I be a summable family of projections on V. Suppose you have two properties, this family should have two properties. Suppose that first is the summation pi I in I, these operators, sum operator should be the identity operator, is summable, therefore, this sum makes sense, and we are demanding that the sum of this family is nothing but the identity operator. And second condition is pi compose pj is 0 if I j are different in different indices. Then what is the conclusion? Then we want to decompose V into direct sum decomposition in such a way that the projections which will come from the direct sum decomposition as above, they will coincide with this given family pi. Okay. Then V is direct sum I in I of image pi. Is the direct sum of the family image pi. These are my UIs, and the given pi is the corresponding projection. For every I in I. This means using a direct sum we have defined a projection, the same projection. So, proof is very easy. So, let us write a proof. So, when we want to check V the direct sum of this, we have to check two things. First is we have to check that V is the sum of this family. That means V is the smallest subspace which contain all these guys. That was the definition of a sum space. And also we have to check that this sum is a direct. That means if you fix one of them and intersect with the remaining sum, that should be 0 space. So, that means image of pi or pj intersection with the remaining sum I in I minus j image of pi, this should be 0. Once we check these two, then it will check the equality here. So, let us check that. So, to check the first equality, I will have to check that. Okay, first what am I checking? First I am checking that this equality. First of all, this is obvious because this is in any case a subspace. So, I have to check that every V belongs here. So, that means I want to check that every V, okay. So, let us check that every V should be written as sum of elements from image Pi and only the finite sum. So, start with any V in V. So, V equal to V is same as identity operator operating on V. But we have given the condition 1 was the summation of Pi is ID. So, therefore, this ID I will replace by summation Pi. We have given that this family Pi is summable. So, therefore, this sum makes sense and that sum is ID is the first property. This evaluated at V, but the way it is defined, this is summation I in I of PIV, and only finitely many of these are non-zero, and by definition, by evidently this belongs to image of Pi. So, that check that every V is an element here. I have written every V as a sum of these guys. So, therefore, we have checked this. This was obvious. Now, we want to check that they do not intersect other than 0. So, we should check that if somebody is in the intersection, then it is actually 0. So, let us take x here on this side and I will check it is 0. So, x we have taken on the left hand side. So, therefore, x we can write it as, because it is in the image Pj, we can write this x as x we have written as Pj of y for some y in V. On the other hand, it is also in summation I in I different from j, image of Pi. When x belong here, that means x is a finite sum coming from each image Pi. So, write x equal to summation is running over I, but different from j, and this belongs to image Pi, means it will be Pi of somebody, Pi of yi, where yi's are elements in V, and I is in I, but I cannot be j, and this means this sum makes sense, means only finitely many of them are non-zero, or almost all of them are 0. So, we have written x like that, and we want to conclude from here x is 0. So, apply Pj to this equation, apply Pj to this equation, apply Pj. So, what will you get? You will get Pj of y, no, Pj of x, Pj of x, which is Pj of y, which is Pj square y, but Pj is projection. So, Pj square is Pj, this is Pj of y, which is x. So, we got x equal to this. Now, I will compute Pj of x by using this sum. So, I apply Pj to this. So, Pj of x, this is this. So, Pj to the sum, Pj to apply to the sum is over I, and I is in I, but I is not equal to j, and Pi of yi, but this is a finite sum anyway, and this is a linear operator. So, I will put that inside. So, this is same as summation I in I different from j, Pj of Pi of y. But this one, this here is nothing but, I will rewrite bracket, this is Pj, by definition Pj compose Pi and then evaluated at yi. That is the definition of the composition. But we have given that this, because I and j are different, this composition is 0. So, this is the map 0 evaluated at yi, which is 0. So, we got x equal to 0. So, that proves the sum is direct, and we have already mentioned that it is the whole V. So, that proves the theorem. So, what we have proved is, given a summable family of projection is equivalent to giving a direct sum decomposition of a vector space. Given a direct sum decomposition, we have the Pj. Now, here I left little small thing to check that if you take, then Pj's are the corresponding projections, but that is clear because in this case the subspaces are image Pi, and therefore, it is clear that the corresponding projections which from this sum which we will get are the given Pj's. What I mean is this. So, that proves the theorem. Now, after the break I will start dual spaces, or let me start a little bit of dual spaces so that we can save some time. Okay. Now, the next subsection I want to start is dual spaces. So, remember, when we have a vector space V is a k vector space, then we have this V star. V star is by definition k linear maps from V to the field k, V to k. So, they are called also, this is also vector space we have checked, this is a k vector space of linear forms on V. Elements of this vector space are called linear forms, and now we want to study V and V star together. For example, we want to check what about the dimensions, dimension V star. Also, given a basis of V, how do you get basis of V star, or the other way, and this study together will sort of lead to duality. Duality is the word used because the dual space is involved in this study. So, and it will also be helpful when you study, for example, in a plane lines that is one dimensional subspace, where do they correspond in V star and so on. So, this interplay between V and V star is called a duality. Okay. So, V star to start with is a subspace of k power V. K power V is a very big vector space. You cannot even write down the basis explicitly. So, and the vector space structure on V star is A f plus B g evaluated at any x is defined A f x plus B g x. This is for all scalars A b. F g are linear forms, and this multiplication and this addition is happening in K now. So, that is the vector space structure, and remember the most important thing we have done in earlier lecture is, if I have, let us take a finite dimensional case first. So, I assume V is finite dimensional, and then we can choose a basis. So, suppose the n is the dimension of V, then we have a basis V1 to Vn, k basis of V, and we have, from this basis we have defined coordinates in V. So, for each I from 1 to n, we have defined this Vi star, which are called coordinate functions. That means, they are maps from V to k, and how are they defined? for any x in V, Vi star is by definition. So take this x and write x in terms of these Vi's. It is a basis. So x will have unique expression A1 V1 plus 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 AN Vn, and you map Vi star is nothing but the AI. I is from 1 to n. I is fixed here, so I do not have to write this here. So this definition makes sense because it is a basis. Note that we cannot do this. This definition does not make sense when it is a generating system or it is linearly independent alone. We are using the fact that it is a basis. Also, one might think that Vi star depends only on this Vi here, but it does not depend alone on that, it depends on the whole basis. So these are called coordinate functions, and we have checked that time they are linear forms on V. That means all these guys are elements of the V star vector space. And now it is very easy to check that, we will check that this Vi is a basis of Vi star, and that will be called a dual basis. So this we will do it after the break.